Okay, so remember before we said there's three things that affect equilibrium. It's pressure, temperature, and concentration. And we done how you can have a disturbance in any of those three and how you can overcome those disturbances by either favoring the forward reaction or the reverse reaction. Now we're moving on to the graphs showing disturbances in either pressure, concentration, or temperature. And this is on page 116 of your textbook. Now, these graphs can be a little bit confusing and complicated, but don't worry too much about it. Just worry about what I'm going to tell you. That is important, and it's just for you to recognize what is happening more than understanding it perfectly. Okay. So remember, when we're dealing with equilibrium, we always have two graphs, always. We're always dealing with a concentration versus time graph, and the second graph is a rate of reaction versus time graph. So anytime we're talking about equilibrium or rate of reaction, there's always going to be a concentration graph and a reaction rate graph. Right, so the first thing we're going to focus on is looking at concentration and how concentration disturbances will be shown in a graph. Right, so we're going to be working with this reaction here, which is nitrogen gas plus hydrogen gas, giving you ammonia gas. Right, and this reaction has delta H of... Right, and the delta H is actually negative here because it's an exothermic reaction. Don't be fooled that they wrote positive 92 kilojoules. Remember last year we done all the different ways you can see whether a reaction is exothermic and endothermic. And since here you have ammonia plus 92 kilojoules, it means this 92 kilojoules is actually part of the products. So if you're making it part of the products, it means you are giving it off, you are releasing it. So you're actually releasing energy, which means it's an exothermic reaction and delta H is less than 0. Okay, so if you see the positive, don't be fooled and think it's endothermic. It's actually part of the products, which means you're releasing energy, so it's exothermic reaction. Okay, so we're dealing here with the exothermic reaction, and we're going to first see how concentration is going to affect any of these reactions. Right, so the first thing is the concentration of nitrogen gas is increased. So that's the first disturbance we're going to deal with. Now I'm not going to explain everything much in detail because you just need to know basics about these graphs. So the first disturbance they did is they increased nitrogen concentration. Now if you look here, nitrogen is the reactant, and if you increase the reactant concentration, to overcome that disturbance, you need to now decrease it. So the only way you can decrease nitrogen is if you favor the forward reaction, which means you're going to now use up the nitrogen, so the reactants will become less and the products will become more. So increasing nitrogen concentration actually favors the forward reaction. Okay. Now, if we have a graph, we can show how this forward reaction is favored. So if you look at this rate of reaction graph, you had equilibrium in the beginning. Remember, in rate of reaction graphs, the forward rate and the reverse rate is equal, so they both touch each other. So they were at equilibrium in the beginning, and then since you added more nitrogen, you favored the forward reaction. So all of a sudden the forward reaction became much more faster. And if you look at this rate of reaction graph, can you see the forward reaction spiked in this graph? It increased drastically. It went straight up because now the forward reaction was favored. And then eventually, after you favored the forward reaction, things started to settle down. The forward reaction then decreased, the reverse reaction then increased until you reach equilibrium again. And that is what Le Chatelier's principle is all about. It's when you have equilibrium in the beginning, like here, you cause a disturbance. After that, you will overcome that disturbance and have equilibrium again. So here, you're going to have equilibrium again for the second time. So that disturbance was basically increasing nitrogen concentration, which means the forward reaction was favored. That's why the forward rate of reaction became higher in the graph. Right, so since you favored the forward reaction, it means you made more products and you made less reactants. Okay, But in order for you to have done that, you first increase nitrogen concentration. So if you had to draw a concentration time graph, you will see that the nitrogen will have been increased initially. So if you look at this concentration versus time graph, you had nitrogen, hydrogen, and ammonia. They were all constant parallel lines, which means they were all in equilibrium first. Then all of a sudden, can you see this green graph is for nitrogen? You had a spike in this nitrogen graph. So all of a sudden, from being parallel, it went straight up and increased. And this increasing graph shows you that nitrogen has been increased. Everything else did not spike. The hydrogen didn't spike. The ammonia didn't spike. The only thing that's shot up in this graph is nitrogen, which means nitrogen concentration was increased. After the nitrogen concentration increased, can you see it decreased again? And then can you see that hydrogen also decreased? And since hydrogen and nitrogen is the reactants, it means if they decreasing, it means the forward reaction is favored. That's why the reactants are decreasing. And then ammonia started to increase after nitrogen increase. So if ammonia is increasing, it means the forward reaction was also favored because ammonia is the product and you're making more product. And then eventually afterwards, the graph became parallel again because all the equilibrium has been reached. So what you need to know here is you had equilibrium in the beginning. All of a sudden, the graph shot up for nitrogen, which shows a rapid increase of nitrogen concentration. After that, reactants decreased, which is nitrogen and hydrogen, and product increased, showing that the forward reaction is favored. And then afterwards, you had equilibrium again. Right, let's look at a different situation. And now in this case, the concentration of N2 is lowered, which means in the first case, we increase nitrogen. Now we are decreasing nitrogen. So now it's the opposite thing happening. So if we're decreasing nitrogen concentration, we need to show that on the graph. So if you look at a graph here, for the concentration versus time graph, can you see the nitrogen green graph? It was at equilibrium, all of them. All of a sudden, this graph just shot down. It went down, right? So because it went down, it means you had a rapid decrease in nitrogen concentration, and that's because the nitrogen has been reduced. They lowered it, or they took it out, right? So you lowered it, and if you are lowering reactant, remember, if you're taking out nitrogen, now you need to make more nitrogen, so the reverse reaction is favored. And if the reverse reaction is favored, you're making more reactants and less product. So, since reverse reaction is favored, it means you're going to make more reactants. And after the nitrogen is lowered, can you see it began to increase? Now it's increasing because now the reverse reaction is favored. And with the nitrogen, the hydrogen is also increasing because hydrogen is a reactant and the reverse reaction makes more reactant. But at the same time, ammonia is decreasing because ammonia is the product, and if you favor the reverse reaction, the product decreases. And if you look at this graph, can you see that we know that now the reverse reaction was favored, but instead of showing it in terms of the reverse reaction, they just show the forward reaction rapidly decreasing. Now, don't worry too much about this one here. Worry more about this. Now, the important thing about concentration, if you either increase it or decrease it, you will always see a spike in the graph. The graph will always rapidly increase, like a straight line going up, if you increase concentration, like this here. Or if it decreases, it will just go down. But it will only go down for one of the reactants or products that you're actually increasing or decreasing, not for all of them, only for one of them. Right, the third type of disturbance you can have is if you increase temperature, so the temperature of the equilibrium mixture is increased. Remember, we said this is actually an exothermic reaction, and we know that increasing temperature favors endothermic reaction. So if the forward reaction is exothermic, it means the reverse reaction is endothermic. So an increase in temperature will favor the endothermic reaction, which is the reverse reaction. So if you're favoring reverse reaction, it means you're making more reactant and less product. So nitrogen and hydrogen will increase and ammonia will decrease. Now let's see how that is shown on the graph. Alright, so turn to page 118. Now if we look at the graphs here, can you see that you had equilibrium in the beginning? all of these graphs were in parallel, hydrogen, nitrogen, and ammonia all in parallel. All of a sudden, nitrogen started to increase, hydrogen started to increase, and ammonia started to decrease. And why is this? It's because we increased temperature, which favored the reverse reaction, so you're making more reactant. So because nitrogen and hydrogen is the reactant, those ones are increasing, and ammonia is decreasing because we're favoring the reverse reaction, so ammonia decreases. Now, can you see this graph here? When we have a disturbance in temperature, there is no spike in this graph. Nothing is rapidly going up or rapidly going down because we're not changing the concentration. All we're doing is changing temperature. So in a temperature disturbance, whether you increase or decrease temperature, you're not going to get any spike in the graph like how you had with a concentration disturbance. It's all just going to either increase or decrease, but there's no spikes. Can you see? Nothing is just rapidly going. Right, and then if we draw the rate of reaction time graph, because the reverse reaction is favored, all of a sudden we had equilibrium before, and now the reverse reaction graph just became very much higher because you increased it. Okay, now I don't want you to worry too much about the rate of reaction graphs. The concentration graphs are more important. Right, now let's look at number 4. The fourth type of disturbance is if the temperature of the equilibrium mixture is decreased. Now you're decreasing temperature. And since the forward reaction is exothermic, it means if you decrease temperature, you are favoring the forward reaction. So you're making more product, which is ammonia, and N2 and H2 are becoming less. Okay, now let's see how this is on a graph. So again, I said, if you're dealing with temperature, you are not going to have any spikes in the graph. Okay, so if you look at the concentration versus time graph, can you see? No spikes. You just have equilibrium at the beginning with the parallel lines. All of a sudden, ammonia started to increase and hydrogen decreased, nitrogen decreased. So because the forward reaction was favored, you made more ammonia, that's why it increased. The reactants both decreased, that's why hydrogen and nitrogen is decreasing. And that's all. There is no more spikes, there's nothing else happening. It is just an increase or decrease. Right, don't worry about this reaction rate graph. Right, let's look at the fifth type of disturbance, and here it's where the pressure of the equilibrium mixture is increased. And remember, we said pressure and volume is inversely proportional. So if you increasing pressure, it's the same thing as reducing volume. Okay, and remember we said increasing pressure favors the reaction that has the least number of moles. So if you're looking at the number of moles here on the reactant side, you have 1 nitrogen, 3 hydrogen, that gives you 4 moles altogether for reactants. And on the right hand side for products, you only have 2 ammonia, so you have 2 moles. So in this case, the least number of moles is on the product side, which is ammonia. So if you are increasing pressure, you're going to go to the direction of the product, which means you're going to favor the forward reaction, which means you're going to make more ammonia and less nitrogen and hydrogen. Now, there is a slight difference when it comes to pressure. When you are having a disturbance in the pressure of a reaction, then the concentration graph kind of looks different. Now, if you look at this concentration versus time graph, can you see that you had equilibrium before? They were all parallel lines. Then, all of a sudden, you have a spike in each one of them. Every one of them are increasing. And that's impossible, because how can all of them increase if only the forward reaction is favored? So nitrogen is increasing, ammonia is increasing, and hydrogen is increasing. Okay, now this only happens when you have a pressure disturbance, because when you're increasing pressure, you are actually decreasing volume, which means concentration is increasing. Right, so just remember, when you have a pressure time graph, you don't need to know the details, but everything is going to increase if you increase pressure. But after it increases, then you're going to start to either increase or decrease based on what reaction is favored. So since the forward reaction is favored here, you're going to make more ammonia. So after this initial spike, now can you see ammonia is increasing because forward reaction is favored, so more product is being made, and the reactants are decreasing, so hydrogen is decreasing and nitrogen is also decreasing because now reactants are becoming less. So when you see a pressure disturbance, you first will have an increase in all of the things, whether it's reactant or product, every single thing in the reaction will increase. But after it increases, then the product will increase if you're favoring forward reaction, and the reverse reaction will, the reactants will decrease after that. Okay, but you will first have this initial spike. Right, and then since the forward reaction is favored, you can see that you have a spike in the forward reaction graph on the rate of reaction graph. Right, let's look at the sixth type of disturbance, which here is the pressure of the equilibrium mixture is decreased, and decreasing volume is the same, decreasing pressure is the same as increasing volume. And we know that if you decrease pressure, the reaction will go to the most number of moles, and in this case the most number of moles is the reactants. So the reverse reaction will be favored, you will make more reactants and products will decrease. Now again, since we have a pressure disturbance, we're going to have a change in everything in the graph. So if we're looking at the concentration versus time graph, can you see everything has decreased? So hydrogen decreased, ammonia decreased, nitrogen decreased, everything, whether it's a reactant or product. And this is because the pressure has been decreased. And if you decrease pressure, it's the same as increasing volume, which is the same as decreasing concentration. Now don't worry what I said there if it doesn't make sense to you. Just know, if pressure decreased, everything will first initially decrease. So everything in the reaction will go down. But after it goes down, then it's going to start changing according to which reaction is favored. So since the reverse reaction is favored, it means now you're going to make more reactants. So that's why now after this, hydrogen increases, nitrogen increases, and then ammonia decreases because that's the product. Okay, so you're first going to have an initial decrease, but then afterwards the reactants increases and the products decreases. Okay, don't worry about this graph. And then finally, the last kind of disturbance, or not actually a disturbance, but the last type of thing is when you add a catalyst to a reaction. Now, a catalyst, remember we said it does not favor any reaction. It does not favor reverse reaction, and it does not favor forward reaction. It does not change concentration of anything. It's not going to make concentration of reactants more or products more or less. Nothing is going to change. The only thing that will happen is that equilibrium will be reached faster, and that's it. That's the only thing. Okay, so if we draw a concentration time graph, it will look exactly like this if we use a catalyst. Can you see? Nothing has changed. Parallel lines, equilibrium is being reached. Nothing has changed in concentration. There's no spikes, there's nothing, because catalyst doesn't change concentration, it just keeps it the same. So can you see? Nothing has changed. But rate of reaction did increase for both of them, so equilibrium is reached faster. So if we have a rate of reaction graph, can you see we have equilibrium first, right? And then both of them were equal, and then all of a sudden both of them increased. Forward reaction increased, reverse rate of reaction increased, and then they were equal again, which means we had equilibrium again. But can you see that this graph is higher than this graph, which means here equilibrium is being reached faster than here, because you added a catalyst. So anytime you have a catalyst, remember, concentration is not going to change, but rate of reaction will increase for both. So you will just have a graph that was lower down, all of a sudden both increases, and then both are equal again. Right, so let's just get a recap of all of these situations again. Now, when you have a concentration versus time graph, and the disturbance in concentration, then if you increase in the concentration of one thing, only that one graph will spike up like this, and then afterwards the graph will either increase or decreasing depending on what reaction is being favored. If you decrease concentration, then you will have a rapid decrease, like a just going down of the graph of one of the things that you took out, and then afterwards it will increase and decrease again. Right, if you have a temperature versus concentration graph, there's no spikes at all. It's just going to be increasing or decreasing depending on what's happening, but no spikes at all. Then if you have, again, temperature, there's no spikes. It's just going to be increasing or decreasing. If you have pressure, disturbance, you're going to, if you have an increase in pressure, pressure is going to increase for everything first initially, and then afterwards it will either increase or decrease. If you have a decrease in pressure, everything will then first decrease and then it will increase or decrease. So if you see one spike, it's concentration disturbance. If you see no spikes, it is a temperature disturbance. If you see a spike or a fall in all the reactants and products, it is a pressure disturbance. And if you see everything staying constant, it is going to be a catalyst.